what exactly forward voltage triggering. Then to explain mainly gate triggering and temperature triggering, that I want to explain the concept of two transistor analysis of SCR. That we'll see what exactly two transistor analysis of SCR. That is, SCR is equivalent to connection of three diodes, or is also equivalent to back-to-back connection of two twin transistors. That is, the total analysis of SCR can be explained using two models. One is transistor model of SCR and other one is diode model of SCR. But mainly we concentrate on transistor model of SCR. That is, SCR is equivalent to, that you go for, concept is two transistor analysis of SCR. Two transistor analysis of SCR. Two transistor analysis of SCR or thyristor. Now we'll see what exactly two transistor analysis of SCR. That is, SCR is equivalent to back-to-back connection of two twin transistors. Back-to-back connection of two twin transistors. Then which are the twin transistors here? PNP and NPN transistors are the twin transistors. That's why SCR is equivalent to back-to-back connection of two twin transistors. Or actually this is nothing but a transistor model. This is explained by transistor model of SCR. This is explained by transistor model of SCR. Clear? Or it is also equivalent to series connection of three diodes, or it is equivalent to series connection of three diodes. Series connection of three diodes. This is diode model of SCR. This can be explained diode model. It is explained by diode model of SCR. But mainly concentrate on two transistor analysis of SCR. That is, SCR is equivalent to back-to-back connection of two twin transistors. Then which are the twin transistors here? PNP and NPN transistors. The another point to remember here, this two transistor analysis or transistor model or diode model is implemented to explain turn on of SCR. It explains two transistor analysis. It explains turn on of SCR. How the SCR will be turned on. Two transistor analysis explains turn on of SCR. Okay. Now I want to prove that how SCR is equivalent to back-to-back connection of two transistors. How it is equivalent to back-to-back connection of two transistors. For that, let us consider the schematic representation of a thyristor or SCR. Let SCR is under forward blocking mode. We are assuming that, let's assume that SCR is under the forward blocking mode. Why you are assuming the SCR is under forward blocking mode means here we want to explain the turn on. What do you mean by turn on of SCR? Bringing the SCR from the forward blocking mode to forward conduction mode. Means let already that SCR is under forward blocking mode. This is P1, this is N1, P2 and N2. This is P1, this is N1 and this is P2 and this is N2. This is anode, this is cathode, this is anode and this is cathode. If SCR is under forward blocking mode means anode is connected to positive plate and the cathode is connected to negative plate. Okay. Now for analysis purpose, let us assume that this exactly divided into two equal parts. If it is exactly divided into two equal parts means then this is P2 layer, this is N1 layer. Okay. This is one transistor. This is NPN transistor. Let this is T2 transistor. This is another transistor. This is T1 transistor. This is PNP transistor. Now this is a emitter of T1 transistor, base of T1 transistor, collector of T1 transistor. Then this is collector of, because it is NPN transistor, exactly opposite. Collector of T2 transistor, base of T2 transistor, emitter of T2 transistor. Okay. Then how to connect these two transistors, that I want to explain. Okay. This is PNP transistor and this NPN transistor. Now how we can connect these two transistors? Then I want to prove that this is a back-to-back connection of two transistors. Understood? But it is a PNP and NPN transistor combination. It is a combination of two twin transistors. Which are the twins? That is PNP and NPN is the twin transistors. Now see, how to connect these two transistors? How to connect these two transistors? Listen please. How to connect these two transistors? This is T1 transistor. This is T1 transistor. Emitter of T1 transistor is connected to which plate? Positive plate. Emitter of T1 transistor is connected to positive plate. This is the emitter of T1 transistor is connected to positive plate. This is T1 transistor. Okay. Next, base of T1 transistor. This is T1 transistor itself now. Base of T1 transistor is connected to collector of T2 transistor. These two are common now. What is this one? Base of T1 transistor. What is this one? Collector of T2 transistor. That is, base of T1 transistor is connected to collector of T2 transistor. Yes. This is base of T1 transistor. This base of T1 transistor is connected to collector of T2 transistor. This is collector of T2 transistor. Next, collector of T1 transistor. This is collector of T1 transistor. Collector of T1 transistor is connected to base of T2 transistor. Yes. Collector of T1 transistor is connected to base of T2 transistor. Okay. Next, this emitter of T1 transistor, emitter of T2 transistor. This is emitter of T2 transistor now. Then emitter of T2 transistor is connected to which plate? Negative plate. That is, emitter of T2 transistor is connected to negative plate. Then we know this. What this terminal in SCR? This is gate. Where the gate is connected, you tell me? Gate is connected at, this is base of T2 transistor, collector of T1 transistor. At that point, gate is connected. Base of T2 transistor, collector of T1 transistor. Base of T2 transistor, collector of T1 transistor. Then it is which terminal? Gate terminal. Then this is which transistor? PNP transistor. This is which one? NPN transistor. Then it is back-to-back connection of two transistors now. That's why SCR is equivalent to back-to-back connection of two twin transistors. Then in order to do the analysis, let this current is this for T1 transistor and T2 transistor, I am giving the current representation. Let this current is IE1, emitter of T1, and this current is anode current. This voltage is anode to cathode voltage. And this is the base of T1 transistor, IB1. This is collector of T2 transistor. This is the collector of T1 transistor. Current representation I am giving here. This is the base of T2 transistor. This is gate current. This is emitter current, IE2. This is cathode current, IK. Now, with this, now I want to do the analysis. Now we'll see what is the analysis based on two transistor model of SCR. Based on this two transistor model of SCR, we want to do some analysis. Now see, in general, this is a generalized equation I am using. In general, for any transistor, we know this, IC equal to alpha IE plus ICB0. This equation we have studied in analog electronics. Okay. This for transistor, this current equation you know, where IC is the collector current, IE is the emitter current, ICB0 is collector to base leakage current with emitter is open. Collector to base leakage current with emitter is open. Where alpha is the current gain. It is a large signal current gain. This equation, you know, this is a generalized equation for common base configuration. Now this equation we want to apply for these two transistors, T1 transistor and T2 transistor. Now tell me, I want to apply this equation for both T1 and T2 transistor. Let for T1 transistor, then you can apply like this. IC1 equal to alpha 1 IE1 plus ICB01, where alpha is the current gain, ICB0 is the collector to base leakage current with emitter is open. We are assuming that now our transistors is under common base configuration, then we are doing this analysis. IC1 equal to alpha 1 IE1 plus ICB01. This is the equation for our T1 transistor. Now, from T1 transistor, you tell me, what is IE1 equal to? IA. Anode current, na? IE1 is equal to IA. This is IE1. This IE1, na? Then this IE1, IA is same. IE1 equal to IA. This IE1 equal to IA. Apply KCL at T1. KCL at T1. Apply the KCL at T1. What is the KCL at T1, you tell me? What is entering current? IE1. What is leaving currents? IC1 and IB1. Therefore, You write IE1 equal to IB1 plus IC1. But what is IE1? IA, okay, is equal to IB1 is equal to IC2, that is IC2 plus IC1. Shall you write like this? Since IB1 is equal to which one? IC2. Yes, this base current of T1 transistor and collector current of T2 transistors are same. IB1 equal to IC2. Then this one also you write like this now. What is IC1 here? IC1 equal to alpha 1 IA plus IC B01. IC1 equal to alpha 1 IA plus IC B01. Let this is equation 1 and this is equation 2. Now for T2 transistor, I am writing the equation for T2 transistor. Tell me, for T2 transistor, you write the generalized equation IC2 equal to alpha to IE2 plus IC B02. But what is IE2 equal to? IK. IE2 equal to IK. This emitter current of T2 transistor is equal to cathode current. These two are same. IE2 equal to IK. If IE2 equal to IK, then what is IC2? Alpha to IK plus IC B01 plus IC B02. Let this is equation 2. Sorry, equation 3. IC2 equal to alpha to IK plus IC B01 plus IC B02. You take IC B02. This we are substituting IE2 equal to IK. Alpha to IK plus IC B02. Then apply KCL at T2 transistor. KCL at T2 transistor. Tell me, what is the KCL to T2 transistor? Which is the entering current? IC2 and IB2. Which is the leaving current? IE2. Shall we write like this? IE2 equal to IC2 plus, that is IE2 equal to IC2 plus IB2. But what is IE2? IK. IK equal to IC2 plus IB2. But what is IB2, you tell me? IB2 means at this point, this is entering current na, this is entering current na, then IB2 equal to IC plus IC1. Then you write IC1 plus IC. Then IK equal to IC1 plus, that is IC2 plus, what is IB2? That you substitute IC1 plus IC. Then IK equal to, what is IC1 plus IC2? Then this IC1 plus IC2 equal to IA. No? This is IA. Yes. Anode current plus gate current. That's why cathode current equal to sum of the anode current plus gate current, since where IC2 plus IC1 equal to IA. Anode current equal to sum of the two collector currents. Okay. Let this is equation 4. Now let's see. This is cathode current. This is IC1 current. This is anode current, and this is IC2 current, and this is cathode current. Now substitute equation 1 and 3 in equation 2. I want to get one standard equation. From that standard equation only, I want to explain the turn-on methods of a SCR. Now substitute equation 1 and 3 in equation 2. Then what is equation 2? IA equal to This one. What is IC1 alpha 1 IA plus ICB01? What is IC2 alpha 2 IK plus ICB02? Alpha 2 IK plus ICB02. Okay. Then IA equal to alpha 1 IA plus alpha 2 IK plus ICB01 plus ICB02. This is anode current. Okay. Now tell me, what is the expression for IA equal to alpha 1 IA plus alpha 2. What is IK? IA plus IZ. This IK I taken IA plus IZ, that I substituted, plus ICB01 plus ICB02. Then you take IA equal to, take IA is common here, alpha 1 plus alpha 2 plus alpha 2 IZ plus ICB01 plus ICB02. Then take IA is common, 1 minus of alpha 1 plus alpha 2 is equal to this alpha 2 IZ plus ICB01 plus ICB02. Now from this we can get one standard equation. What is anode current equal to alpha 2 IZ plus ICB01 plus ICB02 by 1 minus of alpha 1 plus alpha 2. And this is the standard equation in two transistor analysis. From this we can explain any terminal method. To get this standard equation, this I am doing this analysis. Write the expression for T1 transistor, apply KCL at T1. Write the expression for T2 transistor, apply KCL at T2 transistor. Then solve this equation. Then we can get the what is IA. IA equal to alpha 2 IZ plus ICB01 plus ICB02 by 1 minus of alpha 1 plus alpha equal to alpha 2 IZ plus ICB01 plus ICB02 by 1 minus of alpha 1 plus alpha 2. This we are getting. Okay, clear? Now by using this standard equation, now we'll see how to explain the gate triggering method and temperature triggering method. That you concentrate. Yes. That means in two transistor analysis, finally, what is the observation? In two transistor analysis of SCR, then one equation is IA equal to IC1 plus IC2. Anode current is equal to sum of the two collector currents. Then cathode current is equal to IA plus IC, anode current plus gate current. Then IA equal to alpha to IC plus IC B01 plus IC B02 by 1 minus of, this is equation for IA, 1 minus of alpha 1 plus alpha 2. What is alpha 1 plus alpha 2 here? Current gains. Alpha 1 is the current gain of T1 transistor, alpha 2 is the current gain of T2 transistor, IC B01 is the collector to base leakage current in T1 transistor, IC B02 is the collector to base leakage current in T2 transistor. Now by using this standard equation, now we want to explain what is the gate triggering method and temperature triggering method, and I want to prove that within the SCR a positive feedback action is exist. First you start with the gate triggering method. Gate triggering method. Then what do you mean by gate triggering method? Gate triggering means by connecting the gate supply, we can slowly increase the gate current, or we can inject the gate current using gate supply. That means in gate triggering method, by connecting the gate supply, we are increasing the gate current. If IC is increased from this equation, if IC is increased, what about IA? Increases. If IA is increases, what is IE1? Increases, because IA equal to IE1. If IE1 is increases. If IE1 is increases, alpha 1 is also increases. That is current gain is increases due to transistor action. If IE1 is increases, alpha 1 is increases. How it is possible means due to transistor action. Due to transistor action only it is possible. Alpha 1 is increased. Now, tell me, if IA is increased, what about IK also? Cathode current is also increased. Okay. If IK is increased, what is IE2? Increases. If IE2 is increases, what about alpha 2? Increased. If alpha 1 and alpha 2 is increases, what about alpha 1 plus alpha 2? Increases. If alpha 1 plus alpha 2 is increases, what about 1 minus of alpha 1 plus alpha 2? Decreases. If 1 minus of alpha 1 plus alpha 2 is decreases, again IA is increases. Then again IA is increases. If IA is increases, again it is reduces. Again IA is increases. Again 1 minus of alpha 1 plus alpha 2 decreases. Again IA is increases. Okay, then you can remove the gate supply. Then SCR, the current through the SCR is continuously increases. Then it reaches to rated current. Then SCR will be turned on. This type of triggering is called gate triggering method. Concept is very simple. First, what I am doing, just by connecting the gate supply, I am injecting some gate current. Then I will remove the gate supply. If this, even though gate supply is removed, there is a continuously IA is increases. This reduces, IA increases. This reduces, IA increases. Continuously output is increases na. Continuously output is increases means which feedback action? Positive feedback action or regenerative feedback. That's why a positive feedback action is exist. A positive feedback action is exist. That's why a small increase of IC causes large increase of IA. Here large increase of IA means up to rated current. That's the meaning. That's why a small increase of IC, just you can connect some gate supply, then remove the gate supply, then this process will be continued. This process will be continued. Then continuously IA is increases up to rated current. This type of triggering is called gate triggering method. A small increase of IC causes large increase of IA due to internal positive feedback action. This type of triggering is called, this type of turn-on method is called gate triggering. Therefore, a small increase of IC causes large increase of IA. Due to internal positive feedback action. Due to internal positive feedback action. It is called which triggering? Gate triggering. It is called gate triggering method. Like this, a gate triggering is exist, and I proved that within the SCR a feedback action is exist. We can't do anything. Just connect IC, remove the IC. No need of this again gate. Then what happening? This increasing, this decreasing, again increasing, decreasing. Up to what this process will be continued? Up to rated current or up to load current. If it is any load is connected in the SCR. Understood? That's why a small increase of IC causes, even though gate is removed, continuously current is increased. That's the reason I told. Once the SCR start the conduction, no use of gate supply. Remove the gate supply. Then after that, the SCR is continuously conducting because of internal positive feedback action. This type of triggering is called gate triggering. But you have one doubt here, sir. If IE is increases, how the current gain is increases? Yes, that you have the doubt. We know that current gain is alpha equal to output current by input current IC by IE. But as for mathematical analysis, if IE is increases, what the alpha is reduces. This is meaningless. Because we know that alpha equal to IC by IE means if IE is increases, IC is also increases, alpha is also increases. This is correct. That is due to internal positive feedback action. That is due to internal transistor action. This is due to transistor action. What I am telling, it is a common base configuration. If you assume that it is a common base configuration means this is the emitter current, this is the collector current. If the emitter current is increases, collector current is also increases. But the increase of collector current is more dominant than increase of emitter current. If the increase of collector current is more dominant than increase of emitter current, then what current gain is also increases. That is due to transistor action. But just by seeing mathematical, don't say that it is reduces. Okay, mathematically it is, but it is wrong. Technically it is correct. If IE is increases, alpha is up. That's the reason why. If you draw a characteristics between, alpha versus IE, if you draw the characteristics between alpha versus IE, in the case of transistor, then you get the characteristics like this. Up to some value, then it is constant. Then if IE is increases, alpha is also increases. Okay, clear? This about what exactly gate triggering method. That is explained by using two transistor analysis using basic equation. Concentrate. Okay. Then you will see the another method of triggering method, that is nothing but a temperature triggering or thermal triggering of a SCR. How it is explained by using two transistor analysis. Okay. The next one is temperature triggering or thermal triggering. This is the second method of triggering method. Sorry, this is third one. A temperature triggering. This is temperature triggering or thermal triggering. Thermal triggering. This is thermal triggering, temperature triggering or thermal triggering. Thermal triggering. Thermal triggering. Or this process is also explained by thermal runaway or thermal runaway process. Explain thermal runaway of SCR means we can explain like this on thermal runaway. Okay, thermal runaway. This is temperature triggering, thermal triggering or thermal runaway. Okay. Now this method is also explained. This method is also explained by using two transistor analysis, that is basic equation. Basic equation of two transistor analysis. Then we know that IZ equal to or IA equal to anode current equal to alpha to IZ plus IC B01 plus IC B02 by 1 minus of alpha 1 plus alpha 2. 1 minus of alpha 1 plus alpha 2. So, okay. IA equal to alpha 2 IZ plus IC B01 plus IC B02 by 1 minus of alpha 1 plus alpha 2. If temperature is increased, then what is the leakage currents IC B01 and IC B02? Leakage currents are more sensitive to temperature increases. If IC B01 is increased and IC B02 is increases, what is IA? Increases. If IA is increases, what about IE1? Increases. Because IA equal to IE1. If IE1 is increases, what about alpha 1? Increases. If IA is increases, what about IK? Because IK equal to IA plus IC. What is IE2? Increases. What about alpha 2? Increases. Then what about alpha 1 plus alpha 2? Increases. If alpha 1 plus alpha 2 is increases, what about 1 minus of alpha 1 plus alpha 2? Decreases. If 1 minus of alpha 1 plus alpha 2 decreases, again what about IA? Increases. This is internal positive feedback action. Okay, then remove this. Then this process will be continued. Then SCR will be turned on. This type of triggering is called temperature triggering or thermal triggering. Clear? If temperature is increasing, continuously anode current is increases. Continuously anode current is increases means then the SCR starts the conduction. This type of triggering is called temperature triggering or thermal triggering. But don't think like this. We are increasing temperature means this is not the meaning we are heating the thyristor. This is meaningless. We are not heating the thyristor. The increase of temperature is an inherent process. We are not do this method. This is inherent process. That's why temperature triggering or thermal triggering of SCR is an inherent process. No need to increase the temperature for. We don't heat the thyristor. Understood? This is the inherent process. Sir, how it is happening? How the temperature is increases? Concept is very simple. This, instead of turn on of SCR, the SCR is under which state? Forward blocking mode. Clear? It is under forward blocking mode. Now we are bringing the SCR from the forward blocking mode to forward conduction mode. This is one method. Here we are not connecting any gate supply. Understood? Just by temperature only, the thyristor will be turned off. But temperature means we are not heating the thyristor. Temperature is inherent process. Increase of temperature is the inherent process. Now, how it is happening? Let us see. You know that if the thyristor is under forward blocking mode, This is J1, this is J2, and this is J3. The thyristor is under forward blocking mode. Let us assume that. Thyristor is under forward blocking mode. Okay, this is J1 junction, this is J2 junction, this is J3 junction. Okay, if under forward blocking mode, J1 is closed, J3 is also closed, but J2 is open. J1 is closed means having less conductivity or high conductivity. High conductivity. High conductivity. High conductivity means less resistivity. Less resistivity. Because of closed junction, more number of charge carriers, less resistivity. Less resistivity means rho is less than what the resistance offered by the junction in terms of ohms. Under forward blocking mode, J1 junction offers the resistance in the range of ohms because of closed junction. Okay. This is J2 is open. J2 is open means less conductivity because of less number of charge carriers. Less conductivity means less. This is less conductivity means high resistivity. High resistivity. High resistivity. That is, if the resistivity is high, resistance is high, then it offers in the range of mega ohms. J2 junction offers in the range of mega ohms. Then what about J3? It offers high conductivity. Because of closed junction, this junction is closed. That's why high conductivity. It offers high conductivity. High conductivity means resistivity is less. Resistance also less. It is in the range of ohms. Now, let the current at leakage current at J2 junction is IL. Then what is the power loss at J2 junction? Power loss at J2 junction is IL square into R. Then let leakage current is 1 milliampere. That is 1 milliampere. Let us assume that 1 into 10 to the power of minus 3 whole square. R is 100 mega ohms. Then you can get 100 watts. Yes. Under forward blocking mode, because of J2 junction is open, there exists a high power loss. Because of high power loss, we know that if the power loss at J2 junction is increases, then what is the temperature rise? Increases. If the temperature rise is increases, what about the leakage current? Leakage current is increases. If the leakage current is increases, again power loss increases, again temperature increases, again leakage current increases. Continuously temperature is increasing now. A cumulative increase of temperature, this is nothing but it causes cumulative increase of temperature. This is nothing but a thermal runaway. This is called thermal runaway. This is increase of temperature is not a manual process. This is an inherent process. We are not heating the thyristor. Automatically it is happening because of J2 junction is open. A large power loss is exists at J2 junction. Because of large power loss at J2 junction, temperature is increasing, leakage current is increasing, again power loss is increasing, again temperature is increases. That's why it causes the cumulative increase of temperature. Okay, then thyristor will be turned on. But practically the temperature triggering is not allowed because a temperature triggering causes thermal runaway, a cumulative increase of temperature. Because of that thermal runaway, that SCR may be damaged. This is cumulative increase of temperature. This is IL is increases. Again, this process will be continued. This is not the thermal runaway. A cumulative increase of temperature causes permanent damage of the SCR. That's why thermal runaway is not allowed practically. That's the reason why practically, in order to eliminate temperature triggering or thermal runaway, SCRs are mounted on the heat sinks in order to dissipate the heat. Once the heat is dissipated into the environment, the temperature rise is limited. When the temperature rise is limited, there is no increase of the current, then SCR will not turn on. That's why practical. That's why temperature triggering is an inherent process. Temperature triggering is inherent process. Temperature triggering is inherent process. We are not increasing temperature. Is inherent process. Inherent process. Inherent process. Practically, this method is not allowed because it causes thermal runaway and SCR may be damaged. Practically, this method is not allowed. This method is not allowed. This method is not allowed because it causes thermal runaway. Thermal runaway in the sense cumulative increase of temperature. It causes thermal runaway. Thermal runaway. Thermal runaway, and SCR may be permanently damaged. SCR may be permanently damaged. And SCR may be permanently damaged. Then the point to remember, practically SCRs are mounted on heat sinks in order to eliminate the thermal runaway or temperature triggering. Practically SCRs are mounted on heat sinks. Mounted on heat sinks. Mounted on heat sinks. In detail about these heat sinks later on I will discuss. Mounted on heat sinks. Practically SCRs are mounted on heat sinks to eliminate thermal runaway. To eliminate thermal runaway. Thermal runaway. That is to eliminate temperature triggering. To eliminate temperature triggering, practically SCRs are mounted on heat sinks. This method of triggering is called temperature triggering. Clear? This about how to explain gate triggering method and temperature triggering method using two transistor analysis of SCR. Here also positive feedback action is exist. Temperature is continuously allowed, then SCR may be damaged. Don't allow this method. That's the reason why SCRs are mounted on heat sinks, or we are using some external cooling methods also. We can use some external cooling methods. We don't allow this method of triggering. Understood? Temperature triggering causes permanent damage and it also causes misfiring of thyristor. That is not in our control. Okay? This about temperature triggering. That you concentrate. With this, what I explained, what is forward voltage triggering? That method also not preferable. Gate triggering method, that is a preferable method, that is in our control. And temperature triggering method, this method also not preferable. But in forward voltage triggering, are you connected any gate supply? No. Without connecting gate supply, that is the method. In gate triggering only we are connecting gate supply. In temperature triggering, are you connecting any gate supply? No. Because of temperature only it is turned on. That's why the only method we can turn on the SCR by connecting the gate supply is gate triggering. In remaining triggering method, without gate supply also we can turn on. Important for competitive point of view. Okay. In which of the following methods no need of gate supply to turn on the SCR? Like this also SCR will be turned on, but practically not preferable. Except gate triggering method. In remaining all the triggering methods, no need of any gate supply. Only in gate triggering only we can use the gate supply. Clear? Then you go for another triggering method, that is nothing but a light triggering method. Okay, light triggering method. Yes. Concentrate on light triggering method. Yes. A light triggering method means a control light is allowed to fall at J2 junction. That this is P1, this is N1, and this is P2, and this is N2. Okay. This is P1, this is N1, this is P2, and this is N2. This is anode, and this one is cathode. Let initially SCR is under forward blocking mode. This junction is J1, this junction is J2, and this junction is J3. Okay. Then a control light is allowed to fall at J2 junction, that is nearer to inner P layer. A control light is allowed to fall at J2 junction. That means a control light means we can allow the light through some waveguides. A control light is allowed to fall at nearer to J2 junction. Now what happened? This concept can easily understand by using switch concept. Let already SCR is under forward blocking mode. Okay. This is J1 and this is J3 and J2 is open. For this J2, a control light is allowed to fall at J2 junction. We know this concept. A light is falling on the semiconductor device according to photoconductivity. A light is having some wavelength. Because of wavelength of light, if any light is falling on the semiconductor material, then electron hole pairs are generated. That is according to photoconductivity principle. That means if a light is allowed to fall at J2 junction, an electron hole pairs are generated according to photoconductivity. If the electron hole pairs are generated at J2 junction, because of more number of charge carriers at J2 junction, J2 width is reduced. When the J2 width is reduced, at a given forward voltage, J2 is breakdown and SCR comes into forward conduction mode. This type of triggering is called light triggering. That means if light is allowed to fall at J2 junction, an electron hole pairs are generated. An electron hole pairs are generated. An electron hole pairs are generated. That is photoconductivity. Okay. Then, once the electron hole pairs are generated, due to this, width of J2, what happened? Width of J2 reduces. Once width of J2 is reduces, and with given forward voltage, and at a given forward voltage, J2 is breakdown. And SCR comes into forward conduction mode. Then it is called light triggering method. The point to remember, SCRs which utilizes light triggering, is called LASCRs. is called LASCRs. Then that is a light activated SCRs. Light activated SCRs. Light activated SCRs. Then one of the special application of LASCRs is LASCRs are used in HVDC converters. Yes, this LASCR is used in HVDC converters. HVDC converters. We know that in HVDC transmission, at the sending end and receiving end, we are using the converter. At sending end, we can use rectifier. At receiving end, we can use inverter. In rectifiers or inverters, what type of SCRs we are preferring? Means LASCR, that is light activated silicon controlled rectifier. Light activated silicon controlled rectifiers are preferable. This about light triggering method. A control light is allowed to fall at J2 junction. Whenever control light is allowed, because of light is having some wavelength, because of the wavelength of the light, whenever light is fall at J2 junction, an electron hole pair is generated. If any light is falling on the semiconductor material, an electron hole pair is generated. That is nothing but a photoconductivity. If the electron hole pairs are generated, the number of charge carriers at J2 is increases. Once the number of charge carriers at J2 is increases, what is the width of the J2 reduces? It is just like a doping. Okay, width of the J2 is reduces. With a given forward voltage, J2 is breakdown and SCR comes into forward conduction mode. That is called light triggering method. Okay, SCRs which utilizes light triggering is called LASCR, that is light activated SCRs. These light activated SCRs are used in HVDC converters. Okay, this about what exactly light triggering method. Clear? Okay, that you concentrate. That light triggering method you concentrate. The another method of turn on method of SCR is, that is nothing but a dV by dt triggering. That you concentrate. What do you mean by dV by dt triggering of SCR?